Okay. Today, I want to take our maximum and minimum idea and add a twist. Yesterday, we talked about subject to finding the maximum or minimum of a function inside a particular region. So we talked about finding the biggest and smallest value for this particular hyperbolic paraboloid, and we were looking inside some rectangle. Well, now instead of saying I'm in some rectangle, I want to restrict myself to being on a particular curve. The curve g of xy equals some number. Now, if we think about this the way we thought about directional derivatives, I have some curve in the xy plane given by this equation. And that curve gets lifted onto my surface. And I want to find the highest point on the surface. I don't know what this equation g of xy looks like, but let's suppose for the moment in the xy plane, it looks like this. Some function g of xy equals some particular number. I've literally just made up a squiggle here. Somewhere on this xy plane, I also have the function xy. The function xy is a surface. It lives above, below, over the xy plane, right? Instead of drawing that function, I'm going to draw contours for that function. So let me make something up. Let's suppose I had a paraboloid whose cross sections were circles. It'll open upward. My paraboloid opening upward. Then all of its level curves, all of the contours for f of xy might look like circles. Right? Now I'm a horrible drawer, so we'll assume that those are concentric circles of different radii. If I want to know what is the largest level curve that just touches one of these points on G, then I would want the level curve and G to be tangent to each other. There's got to be some other level curve somewhere out here, or maybe out here, where there's a point where the level curve and G are tangent. Okay. Let me think about this a little bit further. If those two just touch each other there, then what do I know about the derivative of G? Remember, the black curve here, that's G of xy equals some number. We think of that as a vector function, it'll have a tangent vector. Yes? And if that tangent vector at this point is also tangent to the level curve, then the two tangent vectors, the tangent vector for f at this curve and the tangent vector for g at that curve, they should be parallel. They might not be exactly the same. One might be longer, one might be shorter, but they should be going the same way. Does that make sense? If these two curves are tangent to each other at this spot, then they should have the same tangent line. Huh. If the tangent lines are the same, then I could draw a perpendicular to that tangent line. Wouldn't it be the same? So not only would they have the same tangent line, they'd have the same normal line. Now, normal line means a normal vector. And that means a vector that's perpendicular to a level curve. Hang on a second. What vectors are always perpendicular to level curves? My fastest descent, fastest ascent. And isn't that my gradient? Page 955, back in the section on gradient, we actually drew, here's the tangent line, there's the perpendicular, that's the direction, that's the gradient. So that means that the gradient of F and the gradient of G need to be parallel at this point. Okay, $64,000 question. How do you know if two vectors are parallel? They have the same direction, right? Same direction means one's a multiple of the other. The gradient of F is some multiple of the gradient of G. But I also want to make sure that I'm on the curve G of XY, right? So I'm going to have to solve simultaneous equations to figure out where my gradients are parallel and where my point is on the curve. Now, this sounds absolutely psychotic, but here's an example. Now, find the points on the curve xy equals 1 that are closest to the origin. First question, what does the graph xy equals 1 look like? it's easier to picture if you just write it y equals. Say again? It's hyperbola. It's y equals 1 over x. But it's the hyperbola that's diagonal, right? Okay. Intuitively, which points on this hyperbola are closest to 0, 0? I would think so, right? The elbow here and the elbow here, because this is supposed to be symmetric, and I'm a lousy artist. So assuming they are symmetric, you would think that if you cut through this at that angle, you'd be fine. So my guess is it should be this point here and this point here. But I want to figure it out. I want to be sure that those are the right points. So what I do is I say, I need a function, f of x, that describes to me the distance to the origin. So picking any point I need a function that tells me how far away that point is from the origin. What function does that? What function tells me how far a point is from the origin? What's the equation f of xy to describe the distance from here to here? Which is, in this case, it's the distance formula. The distance from 0, 0 to the point x, y, distance formula. Square root of x minus 0 squared plus y minus 0 squared. I don't like having a square root in this, so I'm going to cheat. That number is always positive. Square root is never negative. Otherwise, it wouldn't be a plus or minus on the outside, right? You're measuring the distance to something, it's always a positive number. So I'm going to square this instead. I'm going to let f of xy be the square. So now I have this function, the objective, the thing I want to find the maximum of, and I have a constraint. And now my goal is to maximize the objective subject to my constraint. And here's where I take the gradients. In order for me to find the maximum, I need the gradient of f to be parallel to the gradient of g. So I need to know what's the gradient of f. What's the gradient of g? The gradient of f is the partial of f with respect to x, followed by the partial of f with respect to y. Similarly, the gradient of g is the partials of g, first with x, then with y. What expressions go in there? df dx. df dy. dg dx. I'm not worried about the equals k, just this side. And dg dy is x. So here are the three equations I have to solve together. 2x equals lambda y, because I'm multiplying lambda times the gradient of g. 2y equals lambda x, and xy equals 1. Three equations in three variables. Problem is that they're not all linear because that bottom equation has multiplication in it. I've got lambda times y, I've got lambda times x, I've got x times y. These aren't simultaneous linear equations. I can't use a matrix. But I can still solve things here. So how do I figure out what's going on here? Let's take this equation right here. Let's multiply that by y. 2xy equals lambda y squared. Take the equation underneath it and multiply by x. What do I get on the left side? Ah, wonderful. 2xy equals lambda x squared. So those put together, they tell me that lambda x squared equals lambda y squared. But lambda is a number, so I can cancel it out. And that means that x squared equals y squared. What happens if you take a square root there? Or plus or minus, right? Because when I take a square root, I get a plus or minus. X equals y, or x equals negative y. But wait, I have an equation I haven't used yet. This one. So what happens when I go to that equation? Oh, if x is equal to y, then I get x squared equals 1. If x is equal to negative y, I get negative x squared equals 1. That's never going to happen. So I don't have to worry about that. I only have to worry about this. What are the possibilities for x? X is either 1 or negative 1. But y is equal to x. So that means my points are 1, 1, and negative 1, negative 1. And lo and behold, Ben, those are exactly the points in the elbow. Y'all will look at me like I've just slapped you in the face with a wet fish. So talk to me. What's going on? How much further? Yes. I always need to solve the gradient parallel to the gradient, and then I need to include the constraint. Right, right. And if I want to find the points that are closest, so I'm looking for an extreme, right? Well, then the extreme is going to come out where this gradient is parallel to this gradient. and we're on the curve in question. So that's why I need these equations for the gradients and this one for the constraint. Please note the difficult part of this was figuring out what the equation was. I won't disagree with that. That's not at all obvious. But give me more questions. Let's try another one then. This is going to be, again, a different sort of a question. I want to find a window. I want to put a square window, but I'm going to put it in a round hole. So I have this question. Find the largest. What are you doing to me? Largest rectangle that fits inside the ellipse x squared plus 4y squared equals 4. Now, again, my first reaction is, what? Let's draw a picture. So I want to graph this ellipse. But I already told you it's an ellipse. So I just need to know what the x-intercepts are and the y-intercepts are. Then I can make the box and I can draw the ellipse. So what are the x-intercepts? What are the y-intercepts? So now I can say that my ellipse should look something like this. Give or take my crappy artwork. Now, clearly my restriction, my constraint, Nora, my constraint is the size of this ellipse. Because I want you to put a rectangle box in this ellipse. And I want you to make that rectangle as big as you can. How though am I supposed to do that? Except for my artwork, this is an ellipse. It's supposed to be symmetric from left to right. It's supposed to be symmetric from top to bottom. So really, if I can put a big rectangle in this corner, I could just flip it over and then flip it over, right? So I really only need to worry about what's going on in this corner. So let's put a point on the curve. And then clearly I have a rectangle from here. There's my rectangle. Now I take this away and I can flip it over, right? And I can say, oh, well, this rectangle is going to continue down to here, and it's going to continue over to here, and there's my rectangle. The thing I am trying to maximize is the area of this rectangle. So my question to you, based off of this point, what's the area of that rectangle? Aha. The area of the piece in this corner is length times width, that's x times y, and there are 4 of them. So my f of xy, that is the area, is 4xy. Well, now I know what I'm trying to maximize. I know my restriction. In order to use Lagrange's theorem, Lagrange multipliers, what I need to do is take 2 gradients and then write up 3 equations in 3 variables. Remember, that's my constraint up there, being on the ellipse. Okay. Gradient of f, gradient of g. Okay.
I was gonna say that f of x, I was gonna say that f of x, f of y, real quick.
Go ahead.
Oh, no, but I didn't do it yet, I was.
Oh, okay.
Yes.
Sorry. I thought you had done it and you were just reporting it to us.
Sorry.
Partial with respect to x turns this x into a 1. 4 and y stay their constants. Partial with respect to y turns this y into a 1. 4 and x stay their constants. With g, I'm just looking at this part, not the equals 4. Partial of g with respect to x. And partial with respect to y. So here are my 3 equations in 3 variables. I need to multiply one of the gradients by lambda to make them parallel. I'm using lambda because the text uses lambda. I don't care what letter you use. Just don't use x and y or f and g because those already mean stuff. You can call it anything you want. So 4y equals 2ax. And 4x equals 8ay. And I'll make a note over here that a is a constant. And then my last equation, Nora, is my constraint. X squared plus 4y squared equals 4. 3 equations, 3 variables. And now for the hard part. The calculus is easy. The algebra sucks. I need to solve this. Technically, I don't actually have to find the value of a, because up there, all I really want is x and y. To be able to tell you what this point is, and then to figure out my area. I don't actually need the value of a. If I happen to solve for the value of a, that's fine. But I really only need x and y. And looking at this point, What would happen if x was 0? What would happen to my area if x was 0? And the same thing if y was 0, right? My area would be 0 in both cases. So I know that neither x nor y is 0. Which means here, I can actually take these equations and use those two solving for a. Because I could divide by 2x here. 4y equals 2ax becomes 2y over x equals a. Because x is not 0, I'm allowed to divide by it. And similarly, 4x equals 8ay becomes something else equals a. What do I get there? Well, if those are both equal to a, then they're equal to each other. Why does that help me? Yeah, but I can do that right from here. If those two fractions are equal, I can cross multiply, can't I? And if I cross multiply, I get x squared equals 4y squared. Look at my ellipsoid, my ellipse. It's not an ellipsoid, it's flat. Look at my ellipse. Oh, I can replace 4y squared with x squared. Why do I know that x must be the positive square root of 2, not the negative one? We put it in the first quadrant, x is positive. Same thing with y. If I had, instead of replacing the x, the 4y squared with an x squared, if I'd done this in y squared, I'd be able to get a square root there and I'd get y equals, and I'd have to use the positive one because it's in the first quadrant. Oh, wait a minute. Up here, x squared is 4y squared. That means that 2 equals 4y squared. So y squared is a half, or y is 1 over root 2. I now know the coordinates of that corner, which means I know the area of this rectangle. And I know all four corners of it. I know its length, I know its width, I know its area. I found the rectangle. I know its length, I know its height. Why is it 2 square root of 2 wide and 2 1 over root 2 tall? It's not just the first quadrant. The rectangle itself extends both in first and second, as well as in third and fourth. So I have to fold it over to get the other side, and I have to fold top down to get the whole height. It works. Talk to me.
This is a very great question.
In what way?
After we go, something that will be easily substituted into.
Yes, the fact that the algebra works so nicely is absolutely rigged. What happens when the algebra doesn't work nicely? I go to Wolfram Alpha. Ladies and gentlemen, I guarantee you that there will be at least one problem. I will look at the algebra and go, are you kidding me? No, I have a computer. I'll use it. But I need to know what equations to feed it. So if I got to this point and saw these three equations and said, I have the foggiest freaking idea what to do, those three equations go into Wolfram Alpha with the command solve, brace, equation 1, comma, equation 2, comma, equation 3. And that works. Let's see. 4y equals 2ax, comma, 4x equals 8ay, comma, x squared, come out of the superscript, plus 4y squared equals 4. Now, I said we were only going to get the positive values for x and y because I put it up in the upper right corner, but you could just as easily use any other corner. And there we go. Now, I am particularly happy to do this in rigged cases where the algebra isn't going to make my eyeballs want to bleed out of my head. And that's incredibly useful if I move from 2D to 3D. Because we were just looking at f of xy. But there's nothing in here that's restricted to just x and y. If I said instead of just using f of xy, I was going to use f of xyz and g of xyz for my constraint, that would work the same way, only this time I don't get 3 equations in 3 variables. I get 4 equations in 4 variables. I believe it's page 975. Yeah, there we go. Example 4. Find the points on the ball, the unit sphere, I'm sorry, the sphere x squared plus y squared plus z squared equals 4. So the ball of radius 2 that are closest to and furthest from 3, 1, negative 1. What the? Okay, wait a minute. I need to see what's going on here. I need to draw a picture so I understand what's going on. The sphere x squared plus y squared plus z squared equals 4 is the sphere in 3D of radius 2. So there's my sphere of radius 2. right? I'm a crap artist, but there's my wireframe sphere of radius 2. And we wanted the point that was nearest or furthest from the point 3, 1, -1. All right, wait a minute. 3 out the x-axis, 1 out the y-axis, 1 unit down. Here's our point P, 3, 1, 1. My sphere of radius 2. And I've got the point 3, 1, -1. I want the point on the sphere closest and furthest away from this spot. Those should be on opposite sides of the sphere, shouldn't they? They should be at exact opposite points on a diameter of the sphere. The one that's closest, and then keep going all the way through to the one that's furthest away, right? So really what this is asking you, what's the point on the surface of the sphere that's directly under this spot? People, this is the whole idea behind a geosynchronous satellite. Your cell phone satellite that's covering your cell phone towers is staying in the same place over the country, which means it has to match speeds as the Earth rotates, so it stays over the same spot. And that means directly on the other side of the world is a whole section of the world that cannot see this satellite. The darkest spot furthest away from this satellite would be the point furthest from that spot. I'm going to do the same trick. I'm going to make the distance function. This is my restriction. I want to point on the sphere. So this is g of x, y, z right here. And then I'm going to play the same game, and I'm going to say, oh, let's use the distance function, but we'll square it to get rid of the square root. F of x, y, z is the distance squared. So that is x minus 3 squared plus y minus 1 squared plus z plus 1 squared. So when I set up my equations, I need the gradient of f, gradient of f. What's the gradient of f? Say again.
3, that's why it's there.
That's squared. So its derivative is 2x minus 3. And then this is squared. So I get 2y minus 1, and then I get 2z plus 1. Now, all of those are chain ruled, but the derivative of x is just 1, the derivative of y is just 1, and the derivative of z is just 1. Then I need the gradient of g. What's gradient of g? Yay! So now I get 4 equations. I get 2x times the quantity x minus 3 equals 2 lambda x. I get 2y minus 1 equals 2 lambda y. And I get 2z plus 1 equals 2 lambda z. And I get x squared plus y squared plus z squared equals 4. Now, again, you may look at this and go, I haven't the foggiest freaking idea what to do here. But I can tell you one thing that's going to make your life a lot easier. In those first 3 equations, you can cancel the 2's. Let's just do the first equation. X minus 3 is now equal to lambda x. Oh, wait a second. Wait a second. I can solve for x here. I can rearrange this and solve for x. I can get x minus lambda x equals 3. Move this part over here, move that part over there. Factor out an x, and I get x equals 3 over 1 minus lambda. I can do the same thing for y. And I can do the same thing for z. And then it'll all be in terms of lambda. I wrote this down. 1 over 1 minus lambda. And z becomes negative 1 over 1 minus lambda. And then I take all of these expressions and I put them in here. And then I can solve for lambda. And using lambda, I get x and y and z. Now, again, you might look at this and go, I don't want to do this by hand. Great. You have the equations. Take them over to Wolfram Alpha, plug them in, let's go. You'll get the right answer. Which, by the way, if I use the plus square root, I get the one that's furthest away. If I use the minus square root, I get the one that's closest. You can do more than one restriction at a time. If you have more than one restriction, then you'll need to have a linear combination. Gradient of f is equal to something times gradient of g plus something times gradient of h, where h and g are my two restrictions. We're in the subspace spanned by those two gradients. This is the intersection of the two different curves. Now that, unfortunately, is going to require me to solve 5 equations in 5 variables. No, there's no question I'm not doing that by hand. I'm not going to come close to doing that by hand. I'm going to shove that in the computer and walk away. And the example at the bottom of the page here says you're trying to maximize a particular function on the curve that is the intersection between a circle and a cylinder and a plane. So there's this ellipse hanging in space, and I need you to maximize on that ellipse. Bleh. Again, I would say, why the hell do you want to do this? But knowing what the furthest and closest points of approach on an ellipse are exactly what's going to give me the orbital mechanics of the Jupiter satellite that was launched just last year. Where's the furthest point from the orbit of Europa? Where's the closest point for the orbit of Europa? And they're going to orbit Europa not horizontally. They're going to orient that orbit almost vertically. It'll be an ellipse in space so that we'll be able to see the satellite from here the whole time it's orbiting. Useless garbage. I'm never going to see it anywhere. They spent billions of dollars to get the calculus right. Questions? Yes, but because Europa's orbit around Jupiter is very quick, we'll actually see it much more often than not. But we won't have to worry about it being interrupted by Europa itself as well as Jupiter. Okay. So I would like to tell you that we do not have class tomorrow. Tomorrow, I have to be at a teaching demo during our class period. So I will be across the hall in Dr. Burns's class watching a teaching demo for a new faculty hire. If you happen to still be on campus and want to come to the teaching demo, show up. I'll email you the survey link and you can take a survey about the teaching demo. If you're not here, I understand. But I did already create for you tomorrow's lecture. It is right there, scheduled to open at class 9. In addition, the paper notes that I wrote during that video have been uploaded. They will appear at class time tomorrow. So when we don't have class, wherever you are, please feel free over the break to review and watch that. And we'll have question and answer day when we get back. Then Wednesday is Founders Day celebrations. So you should all be getting a schedule for all the stuff. There will be no class on Wednesday. And then your homework will be due Thursday, and we have the exam on Friday. So I hope you enjoy your break. I may or may not see you tomorrow. Ta.